Well, hello and welcome to the 40th and final lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. Finally, we have come to a position to talk about data driven control. Okay. We have seen in the last couple of lectures about data driven simulation first and then data driven analysis, and now we are in a position to talk about data driven control. There are various questions about data driven control that can be asked in the various control questions that can be asked in the setting of data driven in the setting of data driven control. The one that we are going to look at is perhaps the most basic one, namely about stabilization, right. How do you give a state feedback, how do you design a state feedback so that you can ensure that the system is closed loop stable, right. Usually the setting is that your state space equations that are xk plus 1 is equal to a xk plus b uk, and then you define a state feedback control given by xk uk equals fxk. This tells us that xk plus 1 is equal to a plus bf times xk, and then you ask the question whether it is possible to place the eigenvalues of a plus bf by designing this f in such a way that you achieve some goals. Namely, for stabilization you would like to have the eigenvalues of a plus bf within the unit disk, that is the idea. Yeah. But for data driven control we do not have information about this a and b, rather we have information about these guys. We have u0 hat up to ut hat, or t plus 1 does not really matter, and we have information about x0 hat up to xt hat, right. And from here we can actually construct these matrices. I am doing a little I am not being very precise about these numbers, because x1 t will require us to measure this guy to t plus 1, yeah, x0 t is equal to x, these are hats, yeah, or particular trajectory xt hat. So what we have here is that we know that x1 t is equal to b a u0 t x0 t. We assume that u0 t x0 t, this is full row rank. So, the rank of this guy is exactly equal to m plus n, right. So, that is the setting, and from here we would like to understand what happens to this a state feedback. How do you get the closed loop description? So, first to understand the closed loop, you see, if I give a feedback design a feedback matrix f, that feedback matrix is of what size? This has size exactly equal to m cross n, right. Yeah, it is an m cross n matrix, and notice that the closed loop system matrix a plus b f is in fact equal to b a, this matrix that we had, that multiplying f and identity, right. That is how you get a plus b f. But now I notice something about this f times identity. What is the size of this identity? This identity is size n. Okay. Now I notice something. Look at each of the column of this guy. Each column of, see, all of this I am doing because I do not know what b and a is, and I can identify them and then do state feedback and so on. But we have to remember that we want to avoid actually doing this identification business. As much as I can do involving only the measured data, that is good. Yeah, I want to do every computation involving only the data itself, the measured data itself. That is why I am trying to do all these things. Okay. Now, each column of f and identity has, each column belongs to R. Let me know what is this, each column, this is m plus n, right, each column belongs to R m plus n. But we already have a matrix whose image is all of R m plus n. So, that means every column can be written as a linear combination of the columns of this guy. So, that means each column belongs to the column span of the matrix u 0 t x 0 t. Great, no? That is our basic assumption that this is full row rank. This is equivalent to persistency of excitation assumption. So, then that means there exists a matrix F of size what? A number of rows exactly equal to the number of columns in U 0 in this matrix, and that is equal to t plus 1 times what? Times times how many columns does this guy have? It has exactly n number of columns. Yeah, it has exactly n number of columns. So, therefore, n, and then what I have is there exists f such that f identity is equal to u 0 t x 0 t multiplying this matrix scripted f. Okay. So, that means what? That means now x 1 t is equal to b a u 0 t x 0 t. If I now multiply both sides by scripted f, I have this to be equal to a plus b f, right. Let me just not skip this step. This is b a f identity, and that is equal to a plus b f. So, you see from the data itself I have a representation of the closed loop matrix. Yeah, and this closed loop matrix, the properties that I need about the closed loop matrix like eigenvalues and stuff, that can be obtained from this guy. So, all I have to do is I have to find out this scripted f, and then I just plug this guy in here. Yeah, and I have the closed loop system matrix. So, suppose now I ask the question that is it possible to stabilize the system, is it possible to pull the eigenvalues of a plus b f within the unit disk, right. How do I do that? By getting this by designing this f, which in turn means designing this scripted f. Yeah, in order to understand that we need the following. We are going to use, so that is the idea of stabilization through state feedback. So, I have this data with me, this is my starting point, this is the data that I have, and also of course, I have the data u 0 t, which is u 0 hat dot 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 up to u t hat. Yeah, I have this data. From that data I want to find out whether it is possible to get a scripted f, which in turn means to get this f, so that I have a plus b f, which is sure, that is a plus b f, that is the closed loop system is stable. Okay. Now, notice that closed loop system is stable, closed loop asymptotically stable, if and only if a plus b f is what is known as sure. Yeah, that means all the eigenvalues of a plus b f is within the unit disk, yeah, open unit disk, but that is the same as existence of a n cross n symmetric positive definite matrix such that okay, a plus b f p a plus b f transpose minus p is negative definite. That is Lyapunov's theorem for discrete time systems. this transpose and this you can interchange them. This is more useful for us as far as manipulations are concerned, but but both are okay, and that follows from the fact that values of a matrix and its transpose are exactly the same. Yeah, so therefore it is okay to have this. Now we know what A plus BF is in terms of the data. What is it? In terms of the data, A plus BF is given by x1t times this matrix F, which is unknown to us. So let me rewrite that. X1t F P F transpose x1t transpose minus P must be less than or equal to 0 then. Okay. Now I am going to define F times P, I will define as a matrix Q. Okay. F times P is equal to Q. This would imply then x1t, Fp is sitting over here. So, I have a Q here. Now, I have see this F transpose also over here. This means however, that F is equal to Qp inverse, is not it. So, then for this F transpose I can write P inverse transpose, but P is a symmetric matrix. So, P inverse will remain there, and I have Q transpose here. Then I have x1t transpose minus P less than or equal to 0. But now this is very interesting. Yeah. Why is that so? Why is this interesting? Well, this is where this idea of a Schur complement comes into the picture, right. Suppose I have matrices like this. I have A, B, B transpose and C. I have a symmetric matrix like this, and suppose I assume that A is invertible. Yeah, suppose I assume that A is invertible, then I can do some tricks. What kind of tricks? Well, I first do some let us say I do some column operations on this guy, so that this guy becomes 0. What do I do in order to make this guy 0? Let me just do this first. I assume that A is invertible. Okay. Now, I am going to do a column operation on this guy, so that this guy becomes 0. What column operations do I have to do? I keep the first column intact. For the second column, I first multiply by minus A inverse, so that gives me identity, and that I will multiply by B. Okay. And that I will add to the second column. What will be the result? The result of this matrix is as follows: A B transpose will remain intact, because it is just this, and for this it will be minus B, right, plus B. So, this will be 0, and this entry will be C minus B transpose A inverse B, right. Further, I multiply this guy by the transpose of this matrix. The transpose of this matrix will be identity minus B transpose A inverse. Assume that this A is equal to A transpose and C is equal to C transpose, so that this is a symmetric matrix, 0 and identity. That is how I multiply, and that will be the same as multiplying this matrix also by this. Okay. What is the product now of this? So, the first row remains intact by this row operation. The second row is such that this times this plus this is what we are going to get. If I do that, then B transpose A inverse multiplies A. So, A inverse A gives me identity. So, this is minus B transpose, and here I have this times B transpose. So, it is minus B transpose plus B transpose. So, this will be 0, and for this guy it will be 0 times this plus identity times this. So, this will be as it is, right. Now, see what I have done. What has happened in this whole process is the following, that I had a symmetric matrix A, B, B transpose C. This I multiply with identity 0 minus B transpose A inverse identity, and on the right I multiply by its transpose minus A inverse B 0 identity, and that produces a block diagonal matrix that looks like A 0 0 C minus B transpose A inverse B. Okay? That is what it is. This guy is called the Schur complement of A in this matrix. Now, if I assume A is positive definite, right, then you see the following happens. This original matrix gets multiplied by an invertible matrix from the left and right by their transposes. Yeah, this if I call a T, then this is T transpose this matrix, let us say M, this T. So, T transpose M T has this block diagonal structure. Okay. So, now because it is T transpose M T, M is positive definite if and only if T transpose M T is positive definite, but T transpose M T has this structure, out of which I know this guy is positive definite. So, then this T transpose M T is positive definite if and only if this guy is positive definite. Okay. So, then through Schur complement we can do the following, that if there is a block matrix like this 2 by 2 block matrix of which this top left corner is invertible, then I can then this entire matrix is invertible and positive definite, then the entire matrix is positive definite if and only if this Schur complement is positive definite. Okay. Now, we go back to what we were doing. We have something like this which looks eerily similar to this expression C minus B transpose A inverse B. Yeah. So, you see if I put P over here and a P over here and a x1 T Q over here and Q transpose x1 T over here, and I put this matrix, then this matrix is positive definite if and only if this expression is true. Just verify what is the Schur complement of this guy. P is in positive definite, we know that is what our assumption was, P is positive definite. So, if P is positive definite, then I put them down in this matrix form, and it turns out that the Schur complement of this guy is P minus x1 T Q P inverse Q transpose x1 T transpose. Yeah, I think, I hope I have not made a mistake about the sizes. This x1 T is yeah, should be fine, right. This matrix is positive definite, and that is the same as this expression. Yeah, you just put the minus sign and change this sign. So, therefore, that is what we have. Okay. Now, so what we have seen is the following. This is if and only if, sorry, this does not require it. I need this if and only if here, this if and only if with this, yeah, yes, if and only if with this. So, then x1 T f is Schur, that is the closed loop matrix, right. So, closed loop stability. Okay, let me write this down a little below. Closed loop stability, asymptotic of course, if and only if x1 t is sure, which is if and only if p x1 transpose x1 t q transpose, right, that is what it was, q transpose x1 t, q transpose x1 t. Q transpose x1 t, x1 t q just q, x1 t transpose q it should be, isn't it? X1 t transpose, I missed that. There was a transpose here, right? Transpose, no transpose here. P positive definite, right? But what is this P? What is this P? Now I notice the following. So remember what this, so okay, if P is equal to Q, right, if P is equal to Q, yeah, and remember what F is, x0 t times F is equal to identity. See, that is what this is, x0 t times F is equal to identity. So, that tells me if I multiply this guy by x0 t, that will be x0 t times q, and this is identity. So, that means P must be equal to x0 t q, yeah, and likewise I have u0 t f is equal to x1 t, right, sorry, u0 t f, sorry, it is equal to f, is equal to my feedback matrix F, right. So, therefore, F p is equal to Q u0 t that is equal to F p u0 t q, which tells me now F should be equal to u0 t q p inverse, right, and x0 t q is p. Therefore, this is equal to u0 t q x0 t q inverse, right. I think I have not, yeah, that is it. So, then in terms of only one unknown matrix Q, I have the following. I will replace these P's by x0 t q. So, I have closed loop stability asymptotic if and only if there exists a matrix Q of proper size, so that x0 t q x1 t transpose q transpose this x1 t q x0 t q is positive definite, yeah, yes, positive definite. Find out such a q, and then define F to be equal to u0 t q u0 t q x0 t q inverse, that is yours. So, stable if and only if you can find such a q, and with that q define F like this. So, that will be your stabilizing controller. So, stabilization through state feedback is done. Step B. stabilization is done. That's it, and nowhere did we use anything more than the data that we have measured. Okay, so I think we should end this course now. I sincerely hope that you have learned something new. Okay, and you have enjoyed this course. I request you guys to go through the exercise problems as sincerely as you can. All the best for your exams. And before I end, I would like to take this opportunity to thank the entire NPTEL team from IIT Bombay and IISc Bangalore to help build this course, yeah, with all their support. I would like to express my heartfelt gratitude towards all of you, and also thanks to the viewers, thanks to the students who have watched this course from start to finish. Once again, I hope that you have learned something new, and most importantly, you have had fun learning this subject. Okay, perhaps we'll meet sometime in future. Till then, take care of yourselves. Bye.